Good morning, it's Jeremy here. It's Friday, March the 21st, first day of spring. We're in Toronto here on my balcony. Toronto's in lockdown over this COVID-19 virus, but that's not going to stop us from doing our work. And today we're going to look at propagation between a time signal, CHU, located in Ottawa, Canada, and my location here, VE3PKC, in Toronto. So what we're looking at here is a buddy pole vertical antenna, and it's got its base loaded. We're going to go inside and we're going to look at the various received signals from CHU in Ottawa. There's 3 frequencies being transmitted. I think it's 3.33 megahertz. The second frequency is 7.85 megahertz. And the third frequency, I believe, is 14.67 megahertz on 3 different bands. The first frequency uses 3 kilowatts of power into a vertical antenna. The second frequency uses 5 kilowatts of power into a vertical antenna. And the third frequency uses 3 kilowatts. So we're going to look at a receiver here. I'm using an SDR-IQ receiver, and we'll look at the various signal strengths. And then we'll compare that to what we predict with a VOACAP propagation program. VOACAP is used to predict what the reliability and signal-to-noise ratios are between 2 points on the Earth, and they get propagation data from various ionosounds, so they know exactly what the ionosphere is like. So let's go inside and look at the receiver.
CHU Canada, 13 hours, 33 minutes.
Okay, we came inside and we just listened to the recording of 3 frequencies from CHU in Ottawa. We listened to 3.33 megahertz, then we listened to 7.85 megahertz, and then we listened to 14.67 megahertz. Here we have the website for the time station CHU, and it gives you all the information about the station. There are the 3 frequencies, and if you scroll down here, it tells you the exact location in terms of latitude and longitude and the power. So we got 3 kilowatts at 3.33 megahertz and at 14,670, and a little bit higher power at 7,850 kilohertz of 5 kilowatts. So let's go to the VOACAP website. So there's the VOACAP website. What is VOACAP? And there's all sorts of help files. What we're going to do is a point-to-point prediction, so we're going to go into this particular menu here. Okay, so what we have to do now is we have to fill in the data for the transmitter and the receiver. So I'm going to put in, I know the latitude and longitude of CHU, so we'll call that the transmitter. And I know my latitude and longitude, and we'll put that in here. And then what we have to do is we have to set up our antennas, and then we can look at the propagation chart. So I've already done that. So let's go into this screen here. Okay, so what I did is I put in the latitude and longitude of CHU, which I got from their website. That's those 2 numbers there. And then my location in Toronto, I know my latitude and longitude. I put that in there. That's my site, VE3PKC. So
when you put that data in, what it does is it shows you on a map where the transmitter is and where the receiver is. And then it checks the ionosphere and it puts in the various parameters for the various ionospheric levels, for instance, F1, F2, E, and D. And then it gives you the propagation characteristics. So if we go into the next particular slide, in this particular slide here, what we're doing is we're setting up the antennas. Now, if you look at the website for CHU, it says it uses a vertical antenna. So the closest match I found in here on VOACAP was a 3/2 wavelength vertical antenna. So I put that for all the bands. And on my end, I've got a buddy pole, so I put that in as the smallest vertical. It's a 1/4 wave vertical, so I put that in for all the bands as well. And then on the next slide, what we have here is once you run the program, it tells you what the reliability is. Okay, so you need a certain required signal-to-noise ratio depending on your mode of propagation. I've set this up for USB, so if we go back here, I've got SSB. Now, I set the transmitter up, 1,000 watts is the most power that you can have. We know that we've got more power than that. But anyways, that's the way I set it up. And that's the reliability, and those are the particular bands. Like blue, for instance, would be the 80-meter band. That would be close to 3.33. And then pink or orange here is a 60-meter band. And green is the 40-meter, etc. And this is probably the more interesting graph for us at the moment. So I just want to know what the reliability is going to be. So here we've got the various hours in GMT along the circumference here. And there we've got the frequency bands. So let's look at, we did our readings at 9:35, around 9:30 Eastern Daylight Savings Time. So that's 1330 GMT. So there's 1300. So I go in on the wheel here. So 1330 would be in the middle of that column. So you can see that the 80-meter band, which is close to 3.33 megahertz, it's got 100% reliability. And remember from our signal strength there, we could see the signal at 3.33 very clearly, and we could hear it very clearly with no distortion. So that makes sense there. Now the next segment here is the 60-meter band, okay, and we don't have that. And then we move out to 40 meters, which is this segment here. The 40 meters is a 7.85 frequency. Now remember, we could hear that, but very, very poorly. So that corresponds to the 60% here. So probably the 60% is probably a little bit better than what we actually received. And then when we move out to the other frequency, 14.67, which is around 20 meters, we've got nothing, and then we didn't get anything. So at a glance then, this propagation wheel matches the results that we received. Now in our next video tomorrow, we're going to look at this in more depth. There are many more options than VOACAP, so we're going to explore some more of them.